I've been working on a 6502 disassembler for a little while and decided to make a quick video to show the current state. So let me start by opening a new project. You can see there's some preset system definitions over here, but I'm just going to use a generic 6502 and load the tutorial. Now the default load address is 1000, and as it turns out that appears to be about right because it's loading some data from here, storing it at 2000. One thing you'll note is that the disassembler is smart enough to know that a BMI followed by a BPL makes this an always taken branch, which is why the stuff that follows it is disassembled as data rather than as code. This, who knows what this is, so we'll just add a note here so we can come back to it later. Those are just ways to leave messages to yourself, and you can jump right to them anytime you want. So we've got loading at 2000, storing at 2000, jumping to 2000, so this is almost certainly 2000. And sure enough, it now looks like real code. You'll notice that this is now a label. Before it was just a hex address, but since it's now, it can now identify where in the program it is, it's given it a label. This is kind of a stupid label, so let's change that around. It's going to load a byte from 3000. It's going to clamp it to be less than or equal to 4, double it, put it in an index register, and then use that to load some values from these locations down here. And it's going to stick it into this load instruction. So that's self-modifying code, which is always a good thing to call out. So we'll add a comment. You may have noticed this string down here is kind of cut off. That's because I'm sort of squeezing things in for the recording. If you want to see the whole thing, you can just double-click over here, and you get a hex dump with the relevant line highlighted. But back to the code. So this is our input. So we're going to call it input, and we're going to say add a project symbol. Adding a project symbol adds an equate to the top of the file. It's loading, setting the high bit, storing it. We're going to call that output. That's also outside the file. So we've got equates for both of those things. But we still need to deal with this. So this is currently showing up as a string, but it's probably not one. So we're going to change it to be to show it as 1 byte at a time. Now you can see that the strings start at 2030, and the first thing we've got up here is 2030, then 23D, and so on. So this is pretty clearly a set of 16-bit addresses. So we'll just tell the disassembler that. And the disassembler has now assigned labels to the strings and split them out onto separate lines. So this is looking pretty good, but it kind of lacks that old school feel. This is, we'll just put a bunch of stuff in here. But somehow it's just not quite right because, things were much narrower in the old days, and it was always cool to put things into boxes with asterisks. So we'll try that. So you can have multi-line comments. They're automatically word wrapped. You can stick them in boxes if you want. If you don't want, you can, turn that off. Whatever floats your boat. So once you have all this, what do you do with it? Well, first you save your project. Then you go to the assembler screen. And you hit generate. And this creates assembly output suitable for feeding into a cross assembler. And if you don't believe me, run the cross assembler. So it exited with a code of 0, which means success. Sometimes assemblers lie, so we also do a byte-for-byte comparison between the generated output file and the original. Now, if you don't like Merlin, maybe you like CC65. So now everything is in CC65 syntax. We've got local labels, and you can also go ahead and just run that. Now, when you're looking at the output here, maybe you don't like the way it looks. So we also allow you to customize that. So for example, if you are an uppercase kind of person, change everything to uppercase. So now all the opcodes, operands, hexadecimal values, even the values over here in the notes window, they're now all uppercase. If you are a CC65 enthusiast, you can change things to be equal signs and .byte. If you're more of a Merlin sort of person, you got your EQUs, your DFBs. I'm just using this kind of generic data definition 1 byte sort of pseudo-op for everything by default. You can configure it to be however you like. So there's one other set of things that I'd like to show, and to do that I'm going to switch to a program I wrote for the Apple IIgs many years ago called Zippy. And the first thing you'll notice is that there are a lot more definitions. There's a standard set of definitions I have for Apple II ROM location, so that's where all this is coming from. But the one that I want to call out is down here. So the Protos 8 MLI call has been identified as a symbol automatically, as has the function number. And the way that that works is you need a couple of things. First, you need a symbol file that identifies the entry point and the function names. And then you need a bit of code that identifies the JSR for what it is, and then pulls out the necessary symbols. Both of these things are loaded by the project at runtime. This is compiled at runtime. This is not baked into the disassembler. So if you're working on Apple II Protos stuff, you pull these in, and if you're not, then you don't. One other kind of fun thing, if we go to way down here, this is 65H16 code, and here you can see it's using 16-bit addresses. And when you switch in and out, you have to tell the assembler that your register width is changing. And you can see it kind of changing over here in the status flags. But if we come down to this next chunk of code, we can see that it has directed the assembler to use short registers even though there's no SEP instruction. And the reason it can do this is because it knows that the only code that gets to this point has short registers. So it's actually tracking the values of the status flag registers across calls, across branches. So that's about it. Thanks for watching.